this week, the live transcript is working again, so that's good. All right. I hope you had a nice long weekend to get caught up. And if you didn't, then that's totally normal. We're always behind. So this week, we're going to be working through time series. Now, time series are really just a special case of a regression, mostly, where the idea stays the same. Now, let me see here if I can, whoops. Hey, it's not letting me grab it all. And it sounds like I'm sick, but I don't think I am, because I just stopped taking my allergy medication, and I thought, oh, it's winter, we don't need that. Turns out I do. So anyways, sounds terrible, but it's fine. So time series analysis is a special case where we have a time variable on the x-axis. Okay, and so a time series in general is when we have something like this. So we've got some y, so some response variable, and then on our x-axis we've got some time measurement. Okay, that time could be in minutes, it could be in days, it could be in years, weeks, whatever, right? And so there's a lot of different options here, but as long as you have these successive measurements, then we're dealing with a time series. Things like minutes, days, weeks, years, etc. Hours, whatever. Quarters, right? All of those things would be time series. So time series, just in general, is a relationship between the response variable and the x variable. So the explanatory variable is the time. So the explanatory variable is a time measurement. So a time series is a sequence of observations on some variable, so some response variable at successive points in time. There are a couple of things, right? And so, of course, time can be just anything time related. We are not going to consider time periods that are unevenly spaced. So we will only look at time intervals that are evenly spaced. Okay, so just as a little note here, we will only consider time points that are evenly spaced. Okay. There are methods for dealing with unevenly spaced time points, but that's kind of beyond the scope of what we're doing here. So what we're trying to do is we're trying to forecast some behavior, right? And so usually, okay, we have some data. So we have some past data that we can look at, and now we're trying to forecast future data, right? We're trying to forecast, okay, well, what's going to happen in the next quarter, or what's going to happen in the next hour, right? And things like that. So So we're trying to do these forecasts. Okay. There are a couple of different kind of shapes to be able to recognize, or at least patterns that we need to be able to recognize. And so first we need to talk about what they are so that we can say things like, okay, if you see a horizontal pattern, well, what does that mean, right? But then we're going to be able to say that, okay, well, this method only applies if you have a horizontal pattern, or it only applies if you have a trend pattern, or something like that, right? And so first we need to talk about, okay, well, what are these patterns? And then we're going to talk about, okay, how do I know if my forecast was any good, right? We've got a pretty good understanding of, forecasts, especially weather forecasts, but we could do it for a lot of things, right? And so, but for weather forecasts, we understand that if the weather is supposed to be 4 degrees Celsius, let's say, Fahrenheit, no, Celsius makes more sense. If it's supposed to be 4 degrees Celsius out, we understand that that could be a little bit warmer than it's going to be. It could be a little bit colder, right? And so we understand that that forecast is going to have some error attached to it, right? Compared to what we actually see. And so we need some methods where we can talk about, okay, well, the error was reduced here, and so that makes a good forecasting model. All right, so let's first talk about the horizontal pattern, kind of the most basic pattern, I would say. I don't want to say basic, but let's see here. Let me grab the little example graphic here. Maybe I am sick. I don't know. Good thing we're not meeting together. So for a horizontal pattern, really what we're going to see is we're going to see some fluctuations like this, right? So we do see patterns, and we do see some activity here each week, right? And so here, let's see if I can get the pointer up there. So each week we see some changes in the sales for thousands of gallons of gasoline in this case. Okay. Just because it's called the gasoline sales time series plot. So I figured. But what's going to happen is overall, right, what we're seeing is that these points are actually just hovering around some straight line here, right? And so, right, we've got this horizontal pattern, but really they're fluctuating around some constant mean over time. Okay, so here this would be the mean, and I think it was 19. Oh, good. So 19 something. Okay, and so if you have this horizontal pattern, right, you can see that there's activity, but overall that activity is kind of clustered around the mean, right? So it's not over or under too much from the mean at any point. Okay. So we're going to talk about stationary time series a little bit. And so a stationary time series, it means that the process that's generating the data, so in this case, the process would be the sales, right? And so the process that's generating the data has a constant mean, right? And so it's going to essentially remain steady over that period of time that we're looking at, right? And then the variability of the time series is also constant over time, which means that you've got this kind of even spread around the mean as you move along. Okay. you're probably familiar sort of with a trend pattern, and I feel like you would pick up on a trend pattern and maybe even call it a trend pattern without knowing explicitly what it was, right? You would probably look at something like this. Let me see here. Right? You would probably see something like this and say, okay, well, if I had to describe this pattern, right, what would you say? Well, there seems to be an upward trend, right? And so when we see something like this, right, if we had to kind of summarize this behavior, it looks like there's an upward trend. Yeah. And it might be linear, it might be non-linear, right? And those are things that we're going to look into later, okay? But for now, we're just talking about the patterns. Okay, so just keep in mind, there's nothing crazy going on here. It's just like if I asked you, hey, what shape is this? You'd say it's a circle. Well, it's a poorly drawn circle. What shape is this? It's a triangle. Things like that, right? So we're just developing that basic terminology right now. And then once we have that terminology, then we can talk about how do we deal with all these. So here, right, we can see that there's this upward trend, and how it trends exactly, that's not something that we're going to do right now, but just being able to recognize that trend, right? And so we call that a trend pattern. Okay. So a trend, right, is usually due to kind of long-term factors, right? And so, and there's lots of things that could affect the trend, right? And so here we're looking at bicycle sales in thousands of dollars over 10 years. Okay, and so here they're probably just starting out, and so they're not selling a lot of bikes, and then they had a little upswing, and then they had a downtick, and then they've been steady on the rise here. And so if we had to generalize this, we would say there's this upward trend going on here, right, in the bicycle sales for this company. Okay. We could also be dealing with seasonal patterns. Let's see here. So whenever you're in a seasonal business, you're selling fruits and vegetables, you're selling umbrellas in this case, right? If you are selling ice cream, if you're selling heavy jackets, that type of thing, there are a lot of things that we could sell that have this seasonal aspect to it, right? And so what's nice is that it's relatively predictable, right? You know, going into when you are trying to sell maybe winter jackets, right? You know that you're not going to be selling a lot of jackets in June, right? And so you can deal with that. Sorry, I need to go blow my nose. This is insane. I'll be right back. I realized I should have probably paused the video too. Oh, thank you. Okay. So we've got these. I feel fine. It's just my nose is like going nuts. Oh well. Oh yeah. So these seasonal patterns, right? What would they look like? Well, we would see something that would kind of go up and down like this. Notice that there's similarities here to just the horizontal pattern, right? So the difference between a seasonal pattern and a horizontal pattern, that's going to depend on just knowledge about the data, right? So knowledge about how you acquired this data and what it's about, that's going to help you determine whether it's horizontal pattern or a seasonal pattern. The difference between a horizontal pattern and a seasonal pattern is very difficult to see just visually, right? So it's going to rely on knowledge about the data. The difference between a horizontal pattern and a seasonal pattern is very difficult to see in a graph. So we rely on knowledge about the data. We rely on knowledge about the data. Right, to help us determine if it's a horizontal trend or if there's something deeper going on here. Usually we think about seasonal movement as, you know, through the months, right? So that would be our go-to seasonal movement, but they can actually occur over less than a year, or even in a week, right? So we could see, if we look at traffic, for example, right, then we would have this kind of seasonal pattern throughout the week. You know, everyone's going to work, or pre-COVID, let's say. So everyone's going to work Monday morning, and so there's a lot of traffic, and then everyone's getting out of town on Friday. And then on the weekend, there's not very much traffic anymore, right? And then it starts all over on the Monday. Things like that. So it's not necessarily over the entire year, although it often is. Okay. We can have seasonal patterns in less than 1 year durations. Okay. What if we have something crazy, like, what if we have a trend and a seasonal pattern? Oh my gosh. Can you believe it? I bet you can. Let's see here. Okay. So we can do a combination of a trend and a seasonal pattern, right? And so we notice that there seems to be this kind of constant wave of variability, right? And so that's the seasonality part of it, right? And so here, this is the seasonality, whereas this movement here is the trend, right? We still have this kind of upward trend, but it seems to be kind of arching off. And that's still an upward trend, right? And so we've got the seasonality where it's going to fluctuate back and forth as we move through whatever seasons we're talking about, right? Here, period is referring to the quarters. So doesn't really matter, but it's not over a year necessarily, right? It can be less than a year. And so, yeah, so when we have this kind of up-down movement, right, that could be seasonality, it could just be variability, but knowing something about the data, that's going to help us determine if it's seasonality or not. For example, quarterly smartphone sales, well, when do they release new models, right? Then you're probably going to see an uptick. And then if there aren't any new models, then everyone's just kind of waiting for the new model to come out. And then the new model comes out and they go out and buy it. And then you have this uptick and then it drops down, right? And so we can deal with having both, right? But it's going to require pretty sophisticated methods. One thing I will say about time series is it's its own field of study. So what we're talking about here is just gonna like touch down on it and then get out, okay? But you will have a pretty good basic understanding of time series, and that's really all we tend to need, right? If you do find yourself in a situation where you need to be able to model, you know, some crazy situation, then you have the tools to research that, and you'd probably be in a work setting, so then you can talk to your colleagues and they'll know what to do. But most of the time, the techniques that we're going to cover here are plenty, okay? But just be aware that it is a huge field, and it is a very interesting field, right? And so you can imagine all those stockbrokers, they're trying their darndest to forecast those stock prices, right? And so so you can imagine the amount of money that's involved here. A lot of money. So the last pattern that I want to talk about is a cyclical pattern, which is a little bit different, just slightly different. But a cyclical pattern is if we're seeing this kind of alternating sequence of points below and above the trend line that lasts for more than 1 year, right? And so things like housing prices, right? They're always kind of on the up and up, but they will go up and then they'll go down, and then we'll have like an up year and then things will drop down again, right? And so those aren't necessarily restricted to a year, right? And so we would call that a cyclical pattern, right? Even maybe stock prices could be classified as cyclical, right? Because they're not restricted to a year. They could go beyond a year, and that would make it cyclical. Okay. Let me see if there was anything. I have this in here for you to kind of just have a better understanding, but oh yeah, well, this is important. We're not going to talk about cyclical effects. So it kind of goes beyond the scope of this course, and so in this chapter we're not going to deal with it. And so here, cyclical effects are beyond the scope of this course, but of course they happen. I knew there was something I wanted to say here, right? But just be aware that it can happen. Just be aware it can happen. and happens often, right? But we would need more sophisticated techniques. Yeah. Okay. Let's just write a couple of notes here. So when we have a time series, right? So we have a relationship where the explanatory variable is a time variable, right? Whatever time can be weeks, minutes, hours, whatever. And so first thing we do, we have to identify the pattern, right? And then based off of the pattern, we might have tools available to us, or you might have to go digging. But for us, we're going to focus on the horizontal trend for now. Okay. But as soon as we have a trend or a pattern, then I shouldn't say trend because trend pattern is its own thing. But as soon as we have a pattern identified, then what we can do is we can start to think about, okay, well, how should I be forecasting future values, right? And so how can I forecast the next time point and the next time point and the next time point? And so what we need are measurements for the error that we have in our forecast, right? And so that's going to help us judge whether we have a good forecast mechanism or not. Okay. So given a time series, which is a relationship with time as the explanatory variable, a relationship with time as the explanatory variable, okay, we first identify the pattern, and then from there we can pick suitable forecasting methods. We first identify the pattern, then we can try different forecasting methods, try appropriate forecasting methods. So we're going to talk about some of those key forecasting methods, but how do we decide if a forecasting method is good, right? And so to decide or to determine if a forecasting method is good, I'll put it in quotes because it seems like a weird thing to say, but if a forecasting method is good, right, we can apply it to historical data, right? And so we can look at historical data where we already know the outcome, and then if it's forecasting well, in that case, in the historical outcome, then we can apply it to the future. And we don't know how well it's going to forecast, but we have some idea. And as long as it's forecasting well historically, then we feel more comfortable applying it to future forecasts. Okay, so to determine if a forecasting method is good, we apply it to historical data and measure the error in the forecast, and measure the error in the forecast. And I'll put in brackets here, since we already know the outcome, since we already know the outcome of historical data. That doesn't necessarily mean that it's going to perform well in the future, but that's our best kind of measurement tool. Okay, so we need some measurements for the error, and there are a few key ones that we're going to talk about, right? So we don't just look at one error. We look at, you know, how can I what can I talk about in terms of the error? And so that's section 8.2. Let's see here. Oh, let's go to here. So what we're going to do is we're going to look at, I don't have table 8.1, but I have the initial chunk in the table that I've given you. So we're going to look at that. But what we have is we have sales of gasoline over time. Okay, and so what we want to do is we want to just look at, okay, how can I forecast things? What are some of the methods that I could use here? And then how do I pick the best method? Okay, and so the most basic forecasting method is the naive forecasting method, where you just look at the previous week, for example, and that's your forecast. Okay, well, how much in sales did I have last week? That's my forecast. That's what I predict will happen, right? We know that that's not going to be the same, but it is a pretty good forecasting method, right? And so it's called the naive forecasting method. But it's very basic. It's very simple. It's very easy to explain. And so there's benefit there. Right? But for each forecast, you're going to have some error term. Okay. And so here, the E subscript T, sorry, trying not to sneeze here, is the error at time point T. Okay. Oh, and maybe I'll put E subscript T is the error at time point T. Y subscript T is the observed outcome at time point T. Observed outcome at time point T. And in general, Y hat T is the predicted or the forecasted value of Y at time point T. And so remember, Y hat subscript T, I should make that look more like a hat, is the predicted or the forecasted value, predicted or forecasted value at time point T. So if we have a look at this data here, copy. We have the week. So this is the time, right? So here, week is the time variable. Okay, not to be confused with the time series value. This is your Y, right? So this is your Y subscript T. Okay, so that's the actual outcome at that time point t. Y1 is 17, Y2 is 21, Y3 is 19, et cetera, et cetera, et cetera. Okay, so if we use the naive forecasting method, all we're doing is we're taking this value, this 17, and we're using it as our forecast for the next week, right? 21 is being used as a forecast for the following week, for week 3, right? And so this is our naive forecast. I think it has the little, yeah. Okay. So from here, right, we can see that what actually happened in week 2 was we saw 21, right? And that's the sales in thousands, but let's just say 21. Okay, and so what I predicted was 17. So of course I have some forecast error here and an error of 4. Okay, whether it's positive or negative is going to depend on if I overdid the forecast or if I undershot the forecast, right? Over or under predicted the forecast. Okay. And so here, right, the naive method, we just take the previous week's outcome, which we know, right, because that week has already happened. And so I use that as my predicted value for the next week. Okay. Notice that there's no prediction here for the first week, because what would it be? We don't have anything from before the first week, right? And so here we have no prediction. Okay. Which of course means we don't have any forecast error, right? And that's fine. We just have to discount the first week. We use it to use as our forecast for the following week. So we still use it, but we can't get a forecast for every data point. Okay. So some of the things that we could look at are, of course, the forecast error. So the forecast error is going to be the time series value. So the actual value that you saw, YT, minus the forecast value, which is Y hat T. Okay, so 21 minus 17 puts us at 4, right? 19 minus 21 puts us at -2. So let's talk about different ways that we can leverage these forecast errors to try to determine what makes a good forecasting model. Right? We're trying to minimize those errors, right? Of course, that's the same thing as regression, and we're going to end up using regression, but for now, right? We're minimizing those errors, right? And so the first thing that we can talk about is let's talk about the mean forecast error. So the easiest way or the simplest way that we could talk about, okay, well, what was my forecast error here, is what if I average these forecast errors? And so that's what the mean forecast error says. Okay, because we have no prediction and no forecast for the first week, we don't have a forecast error. So when we calculate the average of these forecast errors, right, we have a total of 12 data points, but we actually only have 11 forecasts, right? Because we have n minus k forecasts. Okay. So if we have n periods, so in this case, we have 12 periods in our time series, and k is the number of periods at the beginning of the time series for which we cannot produce a naive forecast. Okay, and so in this case, it's just 1. Later, what we're going to see is, well, what if I used some average of the last 3 weeks, for example, or maybe 2 weeks or 6 weeks or 5 weeks, whatever. We can look at those forecasts and determine which one is going to give us the best forecast. Right. So for now, the most basic forecasting tool that we have is just looking at the previous week, using that as our forecast. Okay. Later, we're going to develop more sophisticated rules. So in this case, k is 1, right? If we kind of zoom in here, it's hard to see, I know, and especially because I kind of drew over it there. How about that? So the sum goes from t equals k plus 1. Okay, and that's because the errors don't start until k plus 1. Forecasting errors start at t equals k plus 1. Oops, that should be k. Okay. Then it just sums up the errors. Okay. And then, of course, if I asked you to find the mean of these forecast errors, what would you do? Well, you would add up the ones that you have and divide by how many you have. In this case, you would notice that you have 11, right? And so you would already do this. And so even though this looks scary, just remember that it's just the mean of the forecast error. Okay. So I think the mean of the forecast error here would be, because we have the sum of 5, and then 5 divided by 11 is going to be, let's see here, 0.4545. Five divided by 11, which is 0.4545, repeating. Okay. The problem is, okay, so this is relatively close to 0. What does that tell me? It's positive, it's relatively close to 0. One of the problems that we run into, again, that we've already seen with the residuals in regression, right, is that, okay, well, if some of these are positive and some of them are negative, they're going to cancel out, right? And so that's why we're going to end up close to 0 most of the time if we're just looking at the mean, right? And so that becomes a problem. So here, because positive and negative forecast errors offset each other, it's not going to be a very useful measure, right? And so what we do is we morph this measure a little bit. Okay. To get more useful measures, we can consider taking the absolute value of the errors, right? So that's one way to make them all positive. You could make them all negative, but we never go that route because it I don't know, that's hard. That's harder, right? So instead, we'll take the absolute value, which it just applies a negative to a negative value, and then it becomes positive, right? And so that's one way to get positive values. Another way is to square the values, right? And so we'll look at both of those options, and then we can look at it as a percentage as well, right? But first, let's focus on the absolute value and the squared values. So to get more useful measures, we consider the absolute values of the forecast errors and then the forecast errors squared. Then the forecast errors squared. Okay. But they're all based off of that mean forecast error. So here, let's look at the absolute value. So the mean absolute error, MAE, or I usually call it the MAD. I don't know, just that's just how I grew up, not really in my undergrad. That's how I have read about it, and so it's hard to shake that once you've called it something, but just know that the MAE and the MAD are the same. Okay, and most people that I've talked to also use the term MAD, so that's why I wanted to highlight that that's an option. Okay, but all it's doing is it's taking the absolute value of the error and it's taking the mean of it, right? And so here, right, take the absolute value of each forecast error, add them up, and divide by how many errors you have in your forecasts, or how many forecasting errors you have. So AE equals MAD, which is add up the absolute values of the forecast errors and then divide by, put brackets around there just to show, I'm just writing out in words what that summation is doing, because it's not as complicated as it looks. It's not as scary as it looks. So you add up the absolute values of the forecast errors, and then you divide by the number of forecast errors, right? So it's just the mean of the absolute error, which is exactly what it's called, right? Usually we call it absolute deviation for MAD, same thing. Oops. What about the mean squared error? So here, now we're squaring the error term, but it's the exact same, right? So now we have this error term, we can square it, and then we can add them up, and then we can divide by however many error terms we have again. So it's still a mean, right? And the MSE is kind of a big player. And so the MSE, mean squared error, is add up the error or the forecast errors squared and then divide by the number of forecast errors. Okay. ET squared over n minus k, well, sum of them, and then over n minus k. In our case, k is just 1, but later k is going to be some other value, right? let's see here. Guess I can scroll up. Okay. So as an example, right, the forecast error, and maybe I'll nab this copy so I can just mark it up just a little bit. Eek, maybe not like that. How about that? Okay. So here, how can I? Okay. Maybe I'll do this. How about this? I'll circle them. And so 5 is the placeholder for the sum from t equals 2 to 12 of the forecast errors. Okay. Whereas 41 is going to be the sum of the absolute value of the forecast errors, right? So now it's the sum from t equals 2 to 12 of the absolute values of the error. And maybe I'll use different color. 179 then is the squared forecast error, which is going to be, once we sum them, is the sum from t equals 2 to 12 of, oops, not the absolute value, ET squared. Right? Once you have those summations, then you can find the average, right, by dividing by 12, or 11, because we only have 11. Right. Find the respective average by dividing these sums, or dividing the sum by 11, right? Okay. The problem with these, so 179, 41, and 5, once I divide them by 11, right, the magnitude depends on, what are we talking about? And we're talking about the forecast of sales in thousands. And so 17 means something, 21 means it's more, right? And so on and so forth. And so that's hard to talk about, and especially it's hard to compare against different units. And I guess I was about to write it down, but then I realized I just have it here anyways. Here. So the size of these two, the mean absolute error and the mean squared error, depends on the scale of the data, right? And so it becomes difficult to make comparisons for different time intervals, right? Or to make comparisons across different time series, or even across different products, maybe. Right? So what if you're trying to decide which product should you be selling, for example? Then you want to have some way where you can compare them, right? Some standardized comparison method. And so then we can talk about the percentage error, right? The percentage error doesn't care about the units anymore because the percentage is the unit. Okay. And so again, this summation looks really nasty, right? But it's, we're going to talk about it, right? And so it's going to be the forecast error divided by the actual value, right? Because we saw that, we know that because we have historical data. And so we can predict or we can forecast, and then, but we also know what actually happened. And so what is that forecast error as a percentage of what actually happened? Times 100, take the absolute value, right? Because you could have a negative error still, right? And so to get rid of that negative error, you would take the absolute value, then add those all up, and then divide by 11 in our case, or n minus k. Okay. So here, the MAPE, fun to say, fun to do, is going to be, I'll break it down in steps because there's kind of too much going on here. But step 1, find ET divided by YT, which is the forecast error at time t, divided by the actual value at time t. So the actual time series value. So the value at time t. So that's your step 1. So basically find the forecast error as a percentage of the actual value. Step 2, multiply each value by 100, okay, to get a percentage. To get a percentage. Step 3, take the absolute value of the percentage. Take the absolute value of the percentage, since the error term can still be negative, right? And so we want to get rid of any negatives because those would just cancel out the positives and then we're left at 0 typically, right? And so that's not useful, right? So we take the absolute value of the percentage, since E subscript T, the forecast error, could still be negative. Okay. Then add up all those absolute value of the percentages and then divide by n minus k. Add up the absolute values of the percentages. And then step 5, divide by n minus k. Divide by n minus k. And in this example, k is 1. In this example, n minus k is 12 minus 1, which is 11. Okay, good. So we have the percentage error, right? So what you can do, or maybe what we'll try is, what if we take the forecast error, right? That's 4 for the first, or for the second week, I should say, right? And then we have our actual time series value, which is 21. So I'm going to find my calculator here. And what if I do 4 divided by 21? Okay, 0.19047, blah, blah, blah. Times that by 100. Oops, sorry. I had to step out there. times that by 100 to get it as a percentage, and that's where that 19.047 blah, blah, blah came from. Okay, let me see if I can, it's not letting me screenshot it. Weird. Okay, that's okay. So here, this is from 4 divided by 21 times 100. Whoops, that's 1,000. Carried away. Okay, and so you could try it, right? You could try -2 divided by 19 and times 100, you would get -10.53. So then, of course, to get rid of those negatives, then you can take the absolute value and then we would add those all up, right? And so then we have, and maybe I'll just copy this again. And maybe, 4 divided by 21 times 100 is 1905. -2 divided by 19 times 100 is -10.53. So then if I take the absolute value of those values, then I get all positives. And where do I end up? I end up here. And what is this? This is the sum from t equals n, k plus 1, I want to say. Yeah, k plus 1. K plus 1 to n of the absolute value of ET divided by YT times 100. And that's the sum, right? So that's just the placeholder for, so this summation is just a placeholder for the sum. Okay, it looks bad, but it's not really. Okay. Copy. So what we've been saying is, okay, well, to build a forecasting method, we're going to use, so we're going to look at historical data and we're going to build a forecasting method based off of that data, right? Just like before, you don't want to overfit your model. So you don't want to make it so good at predicting historical data, so past data, unless you think that it's going to perform equally well in the future, right? And so, just want to highlight that these are really just talking about, okay, how well did it do with the historical data, right? So now you can imagine, what if we want to forecast the sales for week 13, right? So we have up to week 12. What if I want to know what's my prediction for week 13? I have nothing to check it against, right? And so, so I don't know how well it's going to forecast, right? But if I have something that worked for the previous data or for the historical data, then I can feel more confident in my forecast for week 13. Okay. So if we select a forecasting method that works well for historical data, right? And so it hinges on that historical pattern. There's no reason for us to think that that historical pattern would end, right? So it's just going to continue forever, or at least into the future where we want to be predicting. Then our forecast should be pretty good. All right. So there are many ways of forecasting. And so we've only looked at the naive forecasting method for now, right? And that was to introduce things like the MAD, the mean squared error, the MAPE, right? And so it was to introduce those kind of key players in how do we measure how accurate our forecasts are, right? But what if we wanted to do something a little bit more sophisticated, right? And so so far we have only considered the naive forecasting method, and used it to develop those accuracy measures, methods or measurements, maybe accuracy measures, such as the, what do they call it? The MAE or the MAD, the mean squared error, and the MAPE. There are others, but those are going to be our key players, right? So these are our 3 key players. We are going to look at more sophisticated forecasting measures now. And the first one that comes to mind is, what if I just have a running average, right? What if instead of looking at just the previous value, what if I now look at the average of all the previous values, right? And so that's going to be a method. Another one that we're going to get into is, okay, well, what if I just look at the average of the last 3 weeks, right? Or 2 weeks or 5 weeks or whatever. And so all of these are going to make up different forecasting methods. And so I can't remember what it's called. I feel like it's just the total, the running average or something like that. And so we now consider a slightly more sophisticated forecast method. Wait. Let's see here. Wait. Copy. So suppose we use the average of all the historical data available as the forecast for the next period. Okay. And so we can start by developing a forecast for week 2, right? And so that would only have one historical data point, and that would be from week 1, right? But then if we move into week 3, then we have historical data from week 1 as well as week 2, right? And so our forecast for week 3, Y3 hat, is our forecast for week 3. This is the value from week 1, and this is the value from week 2, right? And if we take the average of those, we only have 2 weeks that we're looking at. So of course we're dividing by 2 to get a forecast of 19, right? That's slightly different than our forecast. Our previous forecast for week 3 was 21, right? And so now we're forecasting 19, which looks pretty good, right? And so that's just a fluke that we picked one that was exactly what was happening there. But it does provide slightly improved forecasts. Okay. And so here, let me grab this here, copy. Oh, I see. Got a page break. Notice we get slightly improved forecasts. Okay. So by using that running average, and so here, of course, if we're forecasting for week 8, for example, then our forecast would be the average of the first 7 weeks, right? And so on and so forth. And so then we can still calculate those forecast errors. There's still going to be some negatives and some positives. So we need to deal with that, right? We can take the absolute value for the MAD. We can take the squared error, right, for the MSE, or we can calculate the percentage of the error and take the absolute value of that for the MAPE, right? And so how we calculate those error measurements stay the same, right? As soon as we have a forecast error, then everything just kind of falls into place, right? It's how we get the forecast and how we get the forecast. Well, the forecast error we get the same way, right? Observed minus predicted. It's how we get the forecast that we're trying to figure out the best forecast method. Okay. And so here, right, we have slightly improved forecasts. So we can calculate the MAD, the MSE, or the MAPE using these summations that we have here. And we can map these values, right? 26.81 divided by 11 is 2.44. And if we do a little comparison here, because we're talking about the same units, right, we can compare the forecasting methods because we're talking about the same data, right? And so I'll just add here, since we are using the same data, the measurements are comparable. That wouldn't be the case, right? Except for the MAPE, that wouldn't be the case if we were looking at, you know, the sales of, I don't know, pillows versus the sales of gasoline, right? That they wouldn't compare because they're unit dependent. So the naive method, we get a MAD or an MAE of 3.73, and the average of all the past values gets us down to 2.44. Now, of course, regardless, an error, right, or an error measurement that's low is a good thing, right? And so we see a reduction in all those error measurements, okay? And so as measured by the MAD, the MSE, and the MAPE, the average of all the past weekly gasoline sales provides more accurate forecasts for the next week than using the most recent week's gasoline sales. There there are pros and cons to both of these, right? And so one of the things that we're assuming here is that we have just a horizontal trend, right? And so what can happen is we could have a horizontal trend, but then maybe something happens and it switches, so the average changes. So the average, remember, in the horizontal trend, it's hanging out around an average. And so what if something happens, right? Something in the market happens and that average maybe increases. It still might be a horizontal trend, but maybe something's going on here, right? And so it's still horizontal, but it's around a different average now. So when we have to deal with something like that, then the average becomes really, really slow, right? If you think about the kind of the running average, right, and you think about how the average is affected when you introduce kind of a new value on top of a bunch of other similar values, right, it's going to take a while for that average to adjust. Whereas if you're looking at just the previous, so the most recent outcome as your forecast, then you would really only have 1 week where you had a terrible forecast, right? And then you're back on top, right? And you're using values that are more reflective of your current environment, right? And so that's just something to keep in mind. And maybe I'll write that down before I bring this thing in here. If we have a jump in our horizontal trend, the running average would take much longer, right, to reflect the new horizontal trend than the naive forecast would. The running average would take much longer to adjust than the naive forecast would. Right, that's just something to keep in mind. So there are reasons to use the naive forecast if you suspect that you're going to have these big jumps. And ultimately, you know, we measure these forecasts and we can talk about the MAD, we can talk about the mean squared error, we can talk about the MAPE, but really, it's going to be up to you to know that, oh, I expect a jump to be coming, so I need to be prepared for that, right? So even if historically the running average forecast is doing a lot better, if you expect, so if you have some background knowledge and you expect there to be a jump, then maybe you should switch to a naive forecast, right? That kind of thing. Oh yeah. We'll talk more about this next day, but this is what I was talking about, where we have a horizontal trend and then something happens, there's a shift, right? And then we've got another horizontal trend, but it's along a different average. And I think I'm going to talk my way out of all my time. So if you have any questions, let me know. Otherwise, I'll see you on Wednesday. Stop this.